through one lesson today, and so we're going to focus on 3.3. But actually, to start out, I'm asking you to go back a bit, and I asked you to do these problems as you were waiting here, which actually relates back to what we were doing last class in 3.1, 3.2, and this idea of being able to rewrite our functions, our expressions, into the other form. So if it's in logarithmic form, rewriting it into exponential. If it's in exponential form, rewriting it into logarithmic. And one of the reasons for that is to be able to evaluate, especially when you're dealing with logarithmic expressions. I would say most of us probably are not well versed in logs enough at this point that we can just look at log base 2 of 16 and go, oh yeah, it's this. Maybe a couple of you are, but probably a lot of you, it takes a little bit of thinking through and working it out. And so that working it out usually comes down to, well, what if I rewrite it as an exponent? Because we've worked with exponents a lot longer, our brains wrapped around exponents a little better, we can usually figure out exponents a little easier. Okay, so if we are looking at log base 2 of 16 equal to k, k in this case is just going to represent what is this expression equal to. If I were being asked to evaluate this, what would I get for an answer? But I'm actually writing it as an equation now so that I can do that rewrite. So what would log base 2 of 16 equal to k look like if it was in exponential form? 2 to the power of k equals 16. Now can you tell me what k should be? 4, right? Now it's pretty easy because we're a lot more comfortable with exponentials than we are with logarithms at this point. Okay? How about log base 4 of 1 equals k? What would that look like if I rewrite it? Jeanette? 4 to the power of k equals 1. So then what's k going to have to equal in that case? 0. How about the next one? Dennis, what's that going to look like in exponential form?
Square root of 7 to the power of k.
So k is going to have to equal? Now, this one's a little different because technically I'm starting out in exponential form. So I want to write it into logarithmic form. So what's logarithmic form going to look like? Log base 6 of k equals log base 6 of 20. So what's k got to be in this case?
20. Oh, it's 6 to the power of log base 6. I thought it was 6 times log base 6.
No.
Couldn't trust
This
it.
is little and it's up there on top. That makes it an exponent. Okay? So everybody's comfortable doing that? Switching back and forth and then being able to evaluate like that? Okay. Good. But that's not the purpose of why I asked you to do this. The reason I asked you to do this is because our lesson today is about properties of logarithms. And there's 2 types of properties that we can talk about. One set of properties are what I call the shortcuts. In other words, if we recognize that there's a certain situation going on, then we know that that situation always gives us that result. We don't have to go through the rewrite and the actual work because we just know that situation always gives us that result. So there's that set of properties. Then there's also another set of properties that are more about manipulating logarithmic expressions to rewrite them in a different form that might be more useful. Okay? So when you look at these 4 examples that I started with, do any of them look to you like there might be a shortcut involved? Sam, what's one?
The second one.
Okay, what would be the shortcut? If this happens, then what has to happen?
If you're taking log of 1, then it'll be 0.
Okay, everybody agree with that?
Yeah.
So it's not just about having a base 4, it's about having any base here. If we take the log of some base of 1, it always has to end up being 0, because you always get this situation of your base being taken to some exponent that has to equal 1. Only way that happens is if that k is 0. So here's one of our properties that we can use as a shortcut that says if I ever take the log of 1, no matter what the base is, so it means it can also be a common log, it can be a natural log, anything. If I take the log of 1, it's always going to be 0. Okay? That's going to be a shortcut that I can use. I don't have to go through the rewrite step to get there. Question?
Yes. So if it's log base 1, then it could be like for the one below it, because it's both square root of 7, and that means if the base and the next number are the same, then it's 1.
Right, but we never have a log base 1. Okay?
Oh yeah.
Because if you think exponentially, if my base is 1, I just have a straight line. I don't have anything that's exponential. Yeah, so our b's can't be 1 in the first place, so we're okay. Yep. Okay, any other questions on that one? All right, do you see another one up there that we might be able to come up with a shortcut? Nick?
For the last one,
Okay?
since you have 6 as the exponential and then the logarithm 6, you can kind of cancel those out, and then it's 20 equals k.
Okay, so on this last one, we've got an exponent with a base of 6, but then in the exponent spot, we've got a log that has a base of 6, and so what essentially ended up happening was they canceled each other out and we just got left with the 20. And again, that kind of goes back to the idea of exponentials and logarithms being inverses of each other. If you set them up in a certain way, they actually can cancel each other out for you. Okay? So taking an exponent and then raising it to a power that has a log and the bases being the same is a little bit comparable to having a square and then taking the square root of it. Make sense? So that's another one that we can call a shortcut. We just always know then that if I have this exponential kind of format going on where the bases of my exponent and the base of the log that's in my exponent are the same, they're essentially going to cancel each other out. Okay? Any other shortcuts? Go on.
If it's log base 2 versus the square root of what number is.
Say again?
If it's log base 2, like that's how it is right now, then it's going to be the square root of 16.
Not quite. It is in this case. It would not always have to be. Because I could do a log base 2 of 32, and that's actually 5. It's not whatever nasty number the square root of 32 would be. So it's a good pattern. Yeah. It's just that in this case, it doesn't always work. It's just a one-off kind of thing. Nice try though. That's all right. You're looking at patterns. That's what I want you to see. Any others that you see, Emily?
If you have the log base of a number, it's the third one, and then the number is the same thing that you're taking the log of. It's usually always 1.
It's always going to be 1.
Always 1. Mostly always.
Okay? So in order to be a property, we have to be able to say it's always. Is it going to always?
Yes.
Yes. Because if my base and what I take the log of match, because of how it's going to rewrite, the only way I get this to a power to equal the same thing is if that power is 1. So there's the other shortcut. So this one really is just meant to be there as sort of the example of how do we do the rewrite and we solve for the k and we evaluate. But those other 3 are all examples of sort of shortcut situations where properties can help us to actually speed up the process of doing the problem. We don't have to go through the rewrite step and go through the work. If we can recognize what's going on, and we know this is what's happening, we know this is always the solution. I always get 0, I always get 1, I always get whatever was inside here. Okay? So, the actual properties themselves. log base A of 1 is going to equal to 0 because of what happens when we write the exponential. I would be taking A to some power to get 1, and that would have to be the 0 power. The log base A of A, so there's where we get that matching base with what I'm taking log of, is always going to have to equal 1 because when I rewrite it in exponential, A to the first power has to give me the A. In the third one, we've got the exponential form of it, where I take A to the log base A of x power, and we know that one gave us whatever x was. But we can also do it this way. This says if I have the log base A of A to the x, then the log and the exponent, in a sense, cancel each other out again, and I just get x. Both of these are called the inverse property. Because the result we get is based on the fact that exponentials and logarithms are inverses. They are, in essence, canceling each other out to just leave you with whatever that x value is. Okay? And then what do you think about this last one? We didn't actually have this in our examples, but logic, I think, should prevail here. If the log base A of x is going to be equal to the log base A of y, then what's the conclusion?
X equals y.
X is going to have to equal y. Okay? This also has a particular name to it. It is called the one-to-one property. Now we're actually going to see more of that property next lesson, but it's introduced to us in this lesson, so we'll include it in the list and then we'll work with it more next lesson. Okay, so these are also in your textbook. Unfortunately, they're not on Canvas. Because I noticed the other day when I was at home, I didn't have my books, I was just looking something up on Canvas, like, oh, textbook's on there, I'll just look it up. Somehow when it got scanned, they jumped from
They skipped 3.2.
they went from 3.2 lesson to 3.3 practice, if I remember right. They're like 2 pages into the 3.2 lesson, and then all of a sudden 3.3 practice is there. And I'm like, wait a minute, that's not right. So I'll have to try to get that fixed. But your book itself, if you go home, these properties are all listed there as well. So those are the types of properties I call shortcut properties, where it's just a matter of if you recognize this is the situation, then you know this is always going to be the type of result you get. Okay, makes your life easier, makes the work a little simpler to do. But then we have this other set of properties. And actually some textbooks and some authors, instead of calling these properties, they call them the laws of logarithms to keep them separate. Our book just calls them more properties, whatever. But these are the properties that are more about manipulating the logarithmic expression and rewriting it into something else. And being able to do that rewrite into something else can be really beneficial when you're doing things like solving equations. Because sometimes the form that you get is not going to be really easy to solve. But if I can rewrite it into this other form, then solving becomes much easier. So hopefully these look a little bit familiar to you. You should have at least seen them last year. We have the product property, the quotient property, and the power property. The product property says if I take the log base b of m times n, there's my product, that is equivalent to just taking the sum of the logs of each factor. So taking the log of the m plus the log of the n and keeping the same base consistent. Okay? Now again, if you stop and think about it for a second, you should hopefully once again see that connection between logs and exponents. Because we just got done saying that basically when I evaluate a log, what I'm looking for is what would the exponent be when I changed it to exponential form, right? K was always up there in the exponent, so we were looking for what K would be. Well, if I think about exponents for a second, if I want to take 3 squared times 3 to the 5th, what would I get? 3 to the 7th. Why is it 7?
2 plus 5 is 7.
Because you took the 2 plus 5. You added the exponents. Right? So that's the connection that's happening here. I'm trying to take m times n. I'm multiplying things together. But because logarithms is really about what's happening with the exponents, what I can do is just add the logs of each factor because it's like adding the exponents when we're in exponential form. Similarly with quotient. If I want to take the log of m divided by n, well, what do we do when we are dividing exponents?
Subtract.
We subtract. So I can subtract the log of m and the log of n. And then what happens if I take an exponent and raise it to another power? Then what do?
Multiply.
We multiply. So that's what this is saying. If I'm taking the log of something raised to a power, I can rewrite that as just taking that power multiplied by the log of the a. So again, that connection between logarithm and exponential, it permeates the whole thing. And if you can see those connections, it's going to make understanding all of this a lot easier.
What's the connection for the power property?
Because what do I do if I take an exponent and raise it to another exponent? What do I do with exponents?
Multiply them.
I multiply. So if I'm saying I want the log of this something raised to an exponent, we're saying I'm going to multiply that exponent to the log, so to speak. So the fact that it's exponential here means I need to do multiplying. The fact that I'm dividing here means I need to do subtracting. The fact that I'm multiplying here means I need to do adding. And it ties back to what we do when we're in exponents in the first place. Okay? All right, those look familiar? Kind of remember those from last year?
I remember this test is really hard.
It'll be easy this time. It'll be the second time around, right? All right, so usually what you get asked to do,
That's how it works. Oh no.
usually what you get asked to do with that second set of properties is to be able to expand or condense a logarithmic expression. So if I start with a single logarithmic expression like this, then expanding it means changing it into the sum and difference and multiplying by coefficient kinds of terms that are all being added and subtracted. We're trying to pull it apart, so to speak. Whereas if I get it already pulled apart, where pieces are being added and subtracted and lots of logs are involved, condensing means I'm trying to pull it all back together into a single log. That's usually what we're trying to do. And being able to go from a single log and expanding it, or something that's more spread out and condensing it, is what's going to help us when we get to solving. So, we're going to see what you remember. Go ahead and take a minute. See if you can expand these 3 logarithmic expressions. Try them on your own first. Random mistakes. All right, let's see what we do. Angela, you get the first one. Tell me what you want to write it? Go for it. Try not to put your hand on it, and try not to hold this. So hold here and try not to lean your arm on that. Okay? Those seem to be two things that kind of make it go wonky. Okay. Try.
Yay.
You agree? Is that as expanded as we can possibly get it?
We could blow it up a little bigger.
I didn't say as big as we could possibly get it. I said as expanded as we could possibly get it. Yeah?
Yes.
Okay, good.
We could add a couple
So-
plus one minus one.
When you're doing these, what's going to happen is that most likely there's going to be more than one step to it, more than one property that can be applied to it. If there's so much going on that trying to do it all at once is going to expand your brain, then do it in chunks. And what I mean by that is maybe in this case, you wanted to just deal with the product property first and change it into log of 5 plus log of x cubed plus log of y, and then deal with the fact that, okay, x cubed, I can use the power property and make it into the 3 log of x. Like, there's no problem with you doing a couple steps to get to your final answer, especially if you're a little rusty from last year. Hopefully, you'll get into enough of a groove with this that you can pretty much do it in one shot. But if it takes you a few problems to kind of get back in the groove of that, by all means, chunk it up and do it in a couple of steps so that you're not missing anything and ending up with an incorrect answer. Okay? All right, next one, our natural log one here. Jeanette. What color do you like? Blue. Blue. All right, you're gonna do blue. So you can hold it like right there. Just don't get down in here. And give it a try. Okay, thank you. Is that as expanded as we can get that one?
No.
Oh, what else can we do, Milton?
Put half in the front and take away the.
Oh, yeah. Remember those sneaky little radicals?
Sneaky.
Radicals can also be written as rational exponents, right? So when we see radicals, we're going to need to think about them as exponents in order to be able to work with our properties and expand even more. So if we think about this as really being 3x minus 5 to the 1/2, then what else can we do to expand this?
Half,
One
one,
half.
one to one property.
Yes.
Oh, no. So, power property.
All right? So change the radical into an exponent of 1/2, then use the power property to bring the 1/2 down in front and make it that.
In that case, we keep those parentheses there, because then it would seem like it.
Okay,
Yeah, you
so that's my next question. So now am I expanded enough?
Yes.
Yes.
Yes. So yes, we keep the parentheses there. Here's the temptation. The temptation is to want to go, oh look, ln's sitting out in front of parentheses. Let's just distribute it. The problem is you can't. Okay? And here's the reason why. If you've got your Inspires in front of you, pick up your Inspire. Turn it on. Go to your scratch pad. And I'll get to your question in a second. And I want you to type 3 buttons. Only these 3 buttons. Ready? L, N, enter.
Missing.
Yeah, it's missing. You know why? Because ln by itself means nothing. It's not a value. It doesn't equal anything. ln is a function. It's what we do to something else. Okay? And so it would be like you going around and me saying, okay, so, whoops. It doesn't work on there, does it? It'd be like me saying, okay, so I've got the square root of x plus 2. And you going, oh, well that means it's really the square root and then x plus 2 like this, and somehow this radical sign means something on its own, which we all know is ridiculous, right? Well, ln is also a function, just like square root is a function, and ln by itself, or log, or whatever it is, they're functions you have to do to something else. By themselves, they mean nothing. So this is not a distributive kind of thing, because this ln is not something that we're multiplying to 3x minus 5. It is something we're doing to 3x minus 5. Okay? So don't fall into the trap of thinking you want to distribute when you have parentheses like that. But if 3x minus 5 is the whole thing you're taking the natural log of, you better make sure you keep parentheses around it. Otherwise, you're saying I'm taking the natural log of just 3x and then subtracting the 5 from it. Okay? Question?
Can we split up the 3x?
No, because the 3x is part of this expression where we're subtracting the 5, and so it's not just factors. If it was just 3x, yes, we could split that up another step. But with that minus 5, it kind of mucks things up when we just have to leave it.
If it was minus 6, you could probably pull out a 3.
Right. If it was minus 6, you could, in fact, you could make it the product of 3 times x minus 2, and then split it up more. Yep. But as is, things are expanding, people. Things are expanding. All right. Any other questions on that one? So this is as far as we should go on this one. Everybody okay with that? All right. Next one. Naomi. Got a favorite color? Got a favorite color? Green. I can also go in here and pick out funky things.
You have that marker where it's like it disappears after a certain amount of time.
Those people who
Sorry?
The mark, the special marker where it's like the writing disappears after a certain amount of time.
Lend that to someone who writes their final exam.
This is how they shot it down slow. It was like just slow notations.
It's just
Kind of sounds like it would be Mahoney's invention.
That's specific.
Okay. Agreed? Is that as far as we can expand it?
Yes. Maybe.
What else do you think we can do?
Change the 4 to a 2 and then put a 2 in front of the log.
Okay, you could do that. You definitely could do that, or you could change it to a 2 times 2 and then take log base 3 of 2 plus log base 3 of 2. We're not going to get that crazy.
So
Okay?
you don't want us to.
Yeah, you don't need to. Now, if you do, because you're being cute, cute does not get you points. So, my point is, if you're right, you're fine. But sometimes it's when we get cute that we make the mistake. And if you make a mistake being cute, you're gonna lose points. Okay? So if you're gonna be, like showing off and like, oh, I can take this one more step. I don't mean that meanly, but like, it's not that I'm saying don't think creatively and do that kind of stuff. Just make sure you're doing it correctly, because if you go beyond what's necessary and you make a mistake doing that, then your answer's wrong and you're gonna get points off. So just, risk assessment. Is it worth the risk to go that extra step if it's not necessary?
Always what it is.
All right, everybody good with expanding?
So on the test, if we just leave it like that, it'll be
Yep.
fine.
On a test like this would be great. All right, let's do some condensing. So now we got 3 that are kind of all over the place. We want to bring them back together, pull it together into a single logarithmic expression. Condense it back down.
Is the first one common log?
It is. So is the last one. Joash, you got the first one? So you can hang on to it like here, just don't get it down in there, and then just make sure it presses a bit. Okay, what do you think?
Yeah.
Like it? Alright, good. So we took the 1/2, put it back up here into its exponent spot, and then realized, well, that's really just square root. And then took the 3, put it back up here in its exponent spot, and with the 2 logs being added, that means we're going to multiply those 2 things together, and it's 1 log of that whole thing. I don't necessarily need brackets around this whole thing because of the multiplication. Okay, the multiplication would happen before I did the log. So if you did put brackets around the whole thing, that's fine, but you don't need it in this case since they're being multiplied. Okay? Sean, got the next one? The color? Green. There you go.
That's what I was afraid of.
Okay, what do you think of that one?
Yep.
Good with that? Alright, so again, 2's got to go up into the exponent spot, and then the subtraction indicates we need to set it up as division, so natural log of that whole thing. All right, Iris, want to get a third one shot?
I'm still figuring it out.
Let's give us what you got. Give us what you got, and we'll see how close you get. Third one's a little bit tricky.
I don't know where this 2 is supposed to go on the outside.
Okay, so write what you got. You want to do blue, red, what do you think? Blue, okay. Thank you. Okay, so
Maybe parentheses and then a 2 on the outside.
exactly.
Like that.
There you go. That's it.
Fabulous.
Okay? Because basically up to that point, before she did this, she had done all that. Right? So getting to this point is doing everything that's in the bracket. So now if it's really a 2 times that log, then the property says move the 2 up into the exponent spot, so you end up with that. Okay, that's how you do it. The other way you could do it that would also be acceptable, if this 2 outside of this big huge bracket is freaky to you, and you go, oh, distribute it. You are multiplying by this one. You can distribute this one. So make it 2 log x plus 3 minus 4 log x minus 2, and do it that way. Because what you would end up with then would be x plus 3 being squared and x minus 2 to the 4th, which is what you would get if you actually did numerator and denominator squared. So it'd be the same thing.
So that answer has to be fine?
Sorry?
So that answer would also be fine.
Yep, so that answer would also be fine. Yep, so if you distributed that 2 first and then worked it out, you'd be okay. If that makes it easier, that's fine. Alright, the next one, we're going to do this just really quick because quite honestly, you don't need this formula anymore. If you're using your Inspires, you don't need to use this formula anymore because your Inspire allows you to put any base you want in a problem and work it out. So when I put in, when I choose the log, if I'm trying to figure out what is, I don't know, maybe I want to know what the log base 6 of 25 is. Is that something I'm just going to rewrite and figure out what 6 to some power is to get me 25? No. Okay? But in Inspire, they already have it programmed that I can just say, here's the base I want, here's what I want to take the log of, and boom, give me my answer. So I can put a 6 in for my base, arrow over, put a 25 in the parentheses, hit enter, and watch it give me the same stupid thing. So then you have to do, okay, control enter. There's our decimal, right? So the Inspire, you don't need any type of formula to allow you to evaluate things. But if you're using something other than the Inspire, like your phone, or an old scientific calculator, or a TI-89, or TI-84, something like that. When you look on your calculator, you don't have the option to do any kind of log. You only have the option to do an ln and a log base 10, a common log. Okay? And that's actually how most calculators are. The Inspire is the only one I know of at the moment that allows you to put in any base you want. So that's when you have to have this formula. And what this formula says is, if I take the log base a of x, that is equivalent to taking the log of a different base of the x, as long as I divide it by the log of that base of what the original base was, the a. Now it works for anything. You can change a base A into any base B you want to, but where it's useful is to be able to change it into the bases that are on your calculator. So an ln or a common log. So generally we would say that a log base A of x would either equal common log x divided by common log A, or that the, log base A of x would equal natural log x over natural log A. This is just changing to a b of 10. This is just changing to a b of e. So, would we say the this one was 1.796, more or less? So if I do that on my phone now, I can take 25 common log divided by 6 common log, and I get 1.796. And it doesn't matter if I do common log or ln. I can take 25 natural log divided by 6 natural log, and it's still 1.796. So it doesn't matter which one you use as long as you're consistent on the top and the bottom. Yes?
The 84s can actually do the log base.
Oh, can they? But you have to go like search for it in a menu or something, don't you? Yeah.
You can find it.
Yeah, so the buttons that are on it are just ln and log, but yeah, if you search through a menu, you can find the option to the logs. This one, there is no other option. And if you're anything like me, this is the one you probably have more handy more of the time, right? Like, you're sitting on your bed, you're doing your homework, and you're like, oh, I don't want to get out of my bed to go to my bag to get my Inspire, but I got my phone in my pocket.
Oh,
On the
floor.
Right? So, if you're using something other than the Inspire, this is your formula to evaluate something. But if you're using your Inspire, you don't need this. Okay? All right, last but not least. We're going to make it. So, a lot of what we're going to be doing this year, and especially on things that I know you've at least already seen an introduction to it last year, is that we're going to pick up on that introduction, we're going to build on it a bit, but mostly I want to look at applications. I want to look at how we use this kind of stuff. We don't just learn about logarithms for the kicks and giggles of learning about logarithms. Like, there are applications for it out there. And so I want to show you one really quick that I think is kind of cool. You're going to need your calculators for this, and you might want to write down kind of what we're doing in your tech guide as we do it, because you're going to have something similar to this in your homework. Okay? So, I pulled this right out of the book. And this paragraph says that one method for determining how x and y values for a set of nonlinear data are related is to take the natural logarithm of each of the x and y values. If the points when graphed, after you take natural log, if the points when graphed fall on a line, then you can determine that the x and y values are related to the equation, by the equation, natural log y equals m times natural log x, where m is going to be the slope of this line that your points fell on. So what they're saying is, instead of using the x and y data directly, we're going to take natural logs of all of them, and then the points we plot are actually natural log x comma natural log y, rather than x comma y. And if those points fall on a line, then we can conclude this form of an equation relates x and y for us. And that's what a lot of application kinds of problems are. It's figuring out what's the model that fits the data. Now, there's a lot of different ways to do that. We talk about regression a lot. That's one way. But sometimes regression doesn't always work. or we don't have the type of regression we need in our calculator. So this is another option. So here's a particular example. We've got a table that shows the mean distance from the sun, x, and it's got to be the mean distance because orbits are a bit elliptical, so they're not the same all the time. So it's a mean distance, and the period y, the time it takes for the planet to orbit around the sun. For each of the 6 planets that are closest to the sun. In the table, the mean distance is given in what is called astronomical units, which means the distance from the Earth to the sun is 1. That's 1 unit. So then everything else is measured with respect to that. Okay? So obviously anything less than 1 is closer to the sun, and everything greater than 1 is further away. So we've got our astronomical units where the mean distance is defined as 1 and the period is given in years, and we're supposed to find an equation that relates the x and the y. Okay, so on your calculators, you first need to open up a lists and spreadsheets page, and we need to get our data into our calculator so that we can work with it. So on the table, our first column was our distance and our second column was the period. So that's how we're going to set it up here to keep it consistent. And you need to label your columns. So at the top of column A, actually type in distance. At the top of column B, actually type in period. And then these are the first 5. So go ahead and put those in quick first, and then I'll move it down so you can get the 6th one in. So everyone at least got the 0.387 and the 0.241.
Yes.
So there's the last one. Okay. Now, as we just said from that paragraph, we don't actually want to work with this data. We want to work with the natural logs of this data. So we need to add that to our table. So in column C, we're going to have this be the natural log of the x value. And you need to come up with something to label it that doesn't change from italics. Because if I change to something other than italics, like if I go ln(x) here, see how it changed to bold? That means there's already something in my calculator that has assigned a value to ln(x). And I don't want that to mess things up. So I'm going to do something like, n log x or something like that. Something that's not already a function in my calculator. Okay? And then I'll do the same over here for D. We'll call that n log y. Now, what's cool is that in this spreadsheet setup on your calculator, the second row across here is a formula row. A lot of times we don't put anything in that row because we're just putting data in. But I can now say what I want in this column is based on this particular formula. So here, I'm going to say that I want what's in this column to be equal to ln parentheses of what?
A.
The A, because my x values are in the A column. And when I hit enter, it will autofill for me. I don't have to do each one separately. So every value that's in column A, I now have the natural log of it in column C. And then I do the same thing with D. Equals natural log parentheses B for all my Y values. Okay? All right, so now that I have the data and the values that I want to use, now I'm going to add a page, and I'm going to choose data and statistics. Now if I want to look at what the original points actually looked like, I would go here to distance and over here to period. And so my 6 planets based on my original information look like that. Okay? But what I really want are those natural logs. So I'm going to add another page here quick. Do data and statistics again, and this time I'm going to choose the n log x, and over here for y, the n log y. Did they end up on a straight line?
Yeah.
Yeah, looks like it. So, if they end up on a straight line, then what is it that I need from this line in order to write my model? The slope, right? So I need to know what this line is to get the slope from it. So now I'm going to do my menu, analyze, regression, and I'm just going to choose the linear regression for those points so that I get my equation. And from my equation, I should be able to get my slope, which is about what?
1.5.
About 1.5. So that means that the model for this data is that lny equals 1.5 ln x. Now, if you look in the book, that's as far as they went. They said, there's your equation, that's how x and y are related. Bingo. But I looked at this when I was going through it and went, wait a second. We could take this a step further. How could I take this a step further that might clean it up a little bit?
Oh, it's
Y
but the
equals
one.
ln x to the 1.5.
Right? This is the lesson about properties, right? And actually, I could go even one more step.
Could you?
Y is equal to x to the 1.5.
Oh.
And I actually did check because I saw that yesterday when I was going through this. I'm like, wow, does that really work? Like, is that really possible? Am I missing something here? So I actually went and graphed this on my graph, and then I went to the points on that original one,
And you tried it?
on this one, and I checked the ordered pairs on this one against a y equals x to the 1.5 graph on the other one. They match up.
Whoa.
So why go through this? Because if you just go with this and you try to do a regression, there is no 3/2 exponent regression on your calculator. You're not going to be able to just do this directly with some regression. Because it has to be like a quadratic regression or an exponential regression. Well, this is something that's a little different. So we can still come up with what the relationship is by looking at natural logs instead of looking at the data directly. So I thought that was kind of cool. And there's a problem in your homework that's going to be similar to that. So if you want to take the last couple minutes here and just write down a couple notes in your tech guide to make sure you know how to do what we just did, then you'll be good to go when you get there on the homework.